Again, please. We have a civil department. But anyway, today it's a really great pleasure to introduce, I think, one of the newest faculty members in our department, Dr. Ruda Zhang. He graduated, received his PhD from USC, California, and then he, unfortunately, it was during COVID, he spent a postdoc, a very prestigious postdoc, Statistical and Applied Mathematical Sciences Institute in Durham, North Carolina. And I think you were probably inside most of the time, right, during that COVID period. But then he moved on, and this is where we recruited him from. He was the Philip Griffiths Assistant Research Professor in the Department of Mathematics at Duke University. And he joined us just very recently. He's basically an expert on uncertainty quantification, data-driven engineering, and computational mechanics. So today, he's going to be talking about uncertainty quantification lab, parametric studies of structures via model reduction. Okay, thanks.
All right, thanks for the introduction. Okay. Is it? Okay. All right. So yeah, I'm Ruda Zhang. I joined last fall semester. The plan of the talk today. Okay, so when I submitted the talk, I thought I would just present a regular technical talk, but I feel like I need to explain what uncertainty quantification means. So I added this part. So there are basically two parts. I'll first introduce our lab members, and then the first part is to define what is uncertainty quantification. And the second part will be the original talk. But I think the first one, if I can get you to understand what the first part is, I'll mostly done my job. So this is us. Well, if you figure on the top left is me. This, I just want to hide this. Okay, all right. So Roberta already introduced me. So currently we have Taiwu sitting over there. So he's my current PS student, but we have three members coming and joining. I got a postdoc, Bak Do. He is joining in June. Currently, he's in Kyoto University doing a PhD. And I got also Akash and Toro joining in August. Be my second and third PhD students. So, but they come from India and Nigeria. Wow. So this is about us. It's also not. All right. So so now I got a bit, which is just a bit about myself and our group. I just want to know a bit about you. So how many of you are PhD students? So I assume the others are master students. Okay. How many of you are in civil engineering? Most of them. Okay, I don't have to ask the rest. So for those of you who do research, how many of you identify as doing mostly experimental research? Okay, mostly computational research. What do the other people do? Okay. So what do you do? So no, any of you. So I don't see you raise your hand. So
most of the master students are more coursework only.
Okay, but yeah, the majority of the room are, I suppose I saw just now doing PhD. So yeah, all right. So last question: how many of you have learned probability and statistics? I mean, either course or one course or two courses. Yeah, I'm working with 30% of the room. Okay. Yeah. So uncertainty quantification, of course, builds on probability and statistics. So this is a quite important concept, as I will explain why. Okay. So first part, uncertainty quantification. So this is a quite long term and just pretty. It's a technical jargon. So what is uncertainty quantification? Well, if you break it down, I can break it down into two words: uncertainty and quantification. Well, when I tell people what I do, a few days ago, I met a professor in the math department, and we were at the faculty lunch. He asked me what I do. I said uncertainty quantification. He said, well, I recognize both words, but I don't know what you mean by that. Well, yes, it is two words, and it seems pretty broad. So breaking it down into two words definitely helps. But but we can start with uncertainty. What's your understanding of uncertainty? Okay, you can help me with this. So what's your understanding of uncertainty?
I guess the degree to which you're unsure about whatever your statement is.
So does uncertainty come into any part of your research?
Yeah.
Can you explain?
You could always like make any statement or claim, but there's also a degree to which you don't know if it's true or not. I guess.
Well, you work with Dr. Cleontes, right?
Yeah.
Okay. Well, at least I'm right about one of the things.
Yeah, I guess you could say, I believe concrete strength is 4 KSI. But then there's always a degree of uncertainty to that, or I can say that concrete behaves in a certain manner, but then it doesn't necessarily have to exactly follow.
Yeah. So, but when you do research, does it explicitly factor into how you do your work, or it's just in the back of your mind, but you don't necessarily really do much about it? You can't really come up with a degree of how much error it's going to be.
I don't understand.
Oh, what I'm saying is, well, I think most people understand what most people do recognize that uncertainty is important. It comes in everything. But when you do research, you're a PhD student. So when you do research, does any of those considerations actually affect how you like your publications and that kind of stuff?
Well, yeah, you have to kind of whenever you like present a model, for example, you have to kind of give some justification to how well that model actually like matches what you see in reality, right? Because most of what we like the terms that we deal with, there's a certain degree of randomness, right? Like I can say like generally it's going to be this, but there's always like a normal distribution that we can have, and there's some variation. So yeah, obviously you have to give some justification.
Yeah. That's a very good start. So when it comes to the field of uncertainty quantification, or UQ for short, it's actually pretty narrowly defined. It doesn't cover the entire field of statistics, of course. So this is my short answer for this. UQ is probabilistic methods applied in computational mechanics. Well, you can drop the mechanics into computational science or engineering in general, but overall you got the idea. We use probabilistic methods specifically for computational models. So let me bring you to a bigger picture. So this is a perspective of how we understand the world. This applies to most physical science and engineering problems. So we start from the left. We have a system. We assume there is a ground truth, and we want to know about it. Initially, the original way of studying it is, of course, to do experiments. We take measurements and see what it is. And this is very important. And then we get to develop some mathematical understanding, or call it physical understanding. Usually these models comes in the forms of partial differential equations, but doesn't have to be. So, there are some other forms of mathematical models, even though the PDEs tend to be most powerful, but those Also, you can have simplified physics or empirical relations. These all count as your mathematical understanding. So you have all these models, then they are on paper. So when you have a really complex problem, you want to solve it, you cannot just solve it analytically, then you use computers. So this is what we call a simulator is a computational model of the mathematical models. And then there are many other engineering problems that, well, simulators can solve, for example, PDEs to high accuracy, but they're not necessarily adequate for many types of engineering problems from, for example, when you do optimization and design, say you want to design the wing of an airplane, you need to tweak those simulators, the parameters to the simulators, and usually they're too slow for that. So this is a part of the reason why we want to use surrogates. So surrogates are defined as computational models that approximate the simulator, but they're faster. So you can do things beyond optimization design. You can also do control inverse problems and uncertainty quantification. So this is where in a sense where uncertainty quantification locates in the grand picture of scientific understanding. So this is how I understand uncertainty. I think different people have different definitions of it. And especially the field of UQ, they have very, how to say, peculiar ways of defining partitioning different types of uncertainty. But for me, the more useful way to think about it is, most importantly, error. Errors are everywhere. So I understand error as part of uncertainty because you don't know what it is. And also ignorance. So ignorance is in the lack of knowledge. Either it's in data, which is quantifiable, or understanding, which comes in, you can think of it, your way of thinking about it, or the mathematical or physical model for that. So those things can be not correct. So that, in a sense, it is uncertainty. So both can be called as uncertainty. And quantification, what do we mean by that? So if you learn probability, the standard model for an uncertain object is you have a probability distribution. Of course, you can have a distribution, for example, a Gaussian distribution. That's the entire complete probability description of a number, for example. But we're not limited to that. So we can start with statistics. For example, we know a random variable has a mean, which is number, and the variance. So if you know the variance, you have something about some numbers about the uncertainty. You can also have quantiles, for example, the 5% and 95% quantiles, which defines the end of the distribution. So this gives you a range of possible values. Of course, you have the entire distribution, of course. And well, I also count bounds, that is deterministic bounds about the error as part of the quantification. So this does not necessarily involve probabilistic modeling, but I think it's useful for you to want to know, for example, to certify the error of your calculation. So what is good for? First, if you have uncertainty quantification, you are confident about what you get. So you can use those numbers to certify your result. Perhaps more importantly, once you know how much error you get, you can use that as a guidance to improve your modeling. Ultimately, you won't reduce uncertainty. That's people usually don't like uncertainty. So the reduction of uncertainty is the goal to pursue. All right, so let's put it in a more concrete form. So I teach structural analysis for undergraduates this semester. So let's start with structural analysis. If you think about the crane picture here, so what is the mathematical model behind it? If you trace all the way back, you get this PDE governing the displacement. So the U here is the field of displacement. And this entirety is a partial differential equation that governs any type of deformable body. It can be either linear elastic or nonlinear elastic or plastic. So that comes in, you have the constitutive relation here. Either way, this is a very powerful PDE. That being said, there are many things, so this PDE defines many problems. So this is, in a sense, universal. But does it really solve the deformation problem? It doesn't. There are many things that you need to provide to it. So here, the U is displacement we want to solve. What we don't know. We don't know, for example, so the constitutive relation is something you need to provide at every particular point of the structure. And B is the body force. And this is the computation domain. Well, this does not complete the problem. You have boundary conditions. So you have boundary conditions on displacement and also on loading. So this completes the problem. And you see everything in blue are the information you provide to the PDE before you can actually solve it. Still, currently so this is what we define input to the model. It combines geometry, loading, and material properties. And the output we want is displacement. Still, this is still mathematical. We are even providing all the information, we're still working on papers. So we still couldn't just get the result. So, if we take it in a more abstract sense, putting A and U together, then you can think of A defines a differential operator, and the U is the result. If you invert the D, the differential operator, you get what is called a solution operator. So this is in a FA equals to U, perhaps is a more clean way to think about the model as a mapping. It maps your input, which can be thought of a collection of functions, to your displacement, which is also another function. So in this sense, we call it operators. Just in so operator by which I mean it maps functions to functions, and by function I mean it maps from finite dimensional object numbers to finite dimensional objects.
So this question may not be relevant to the quantification, but what stress are you referring to there in the first equation? What stress?
So it's so it's a CEU. So you apply the displacement to calculate the strain, and then you apply it to
I understand, but in large deformation there are different types of stresses. The true stress is Cauchy stress. That is not true stress. So what stress are you writing there? So in fact, I can write down my equilibrium equation as divergence of P, which is first field of the curve stress plus B is equal to 0. Is there any reason why you put deformation gradient times the stress? The equilibrium equation is divergence of P plus rho B is equal to 0, where it's a Cauchy stress, or divergence of first field of the curve stress plus rho B is equal to 0. Why do you have extra gradient deformation?
That first term doesn't go longer. What you're saying.
It's not important to the overall uncertainty quantification, but from a mechanics point, because I teach advanced mechanics of materials, we just started divergence of B plus rho B is equal to 0. So why do you have the deformation gradient there?
Well, perhaps I can figure this out after the talk with you. Right.
And next one is related to your uncertainty quantification, but there could be uncertainty even in the geometry, right? I may not.
Yeah.
So you also consider in your model uncertainty in the geometry and the boundaries.
Yeah. So the geometry is considered part of the input to the model.
Okay, but it can also be a random variable.
Yeah. Well, currently we haven't defined anything random yet. Well, we just consider that as deterministic input.
Since it's a discussion, I could maybe ask one thing also, and this is fine what you're doing, but the way I look at it, when you explain uncertain quantification as a field, my limited understanding is that some of the really interesting problems are when you don't even have the equation.
Yeah.
In other words, you have to come up with an assessment of something, some decision, and you need to quantify your level of confidence in that decision, where you may have really not even the equations that govern the problem, right?
Yes.
So it's actually quite a wider field than just putting equations in and then trying to come up with some stochastic
Yeah.
dealings of the equation.
Yes, I understand. I also agree with you, but I'll come to that.
Okay,
Yeah.
I think that's the most exciting part.
Yeah. Okay, so previously we have this differential operators that is just exists in the continuous function space, but in practice we solve things using finite elements. We discretize the space, especially we don't really resolve every single spatial detail about the structure. We simplify a lot and then get into the numerical model and solve it. So this is how we do it in computational structure analysis. So this is just one example. So think about what it means for uncertainty quantification. Previously, we defined this F, which is the mapping from your input to output. We can understand this as a system. Of course, this theta means that potentially there are some parameters which you can separate from the input, but we can also consider x and theta to be both inputs. That is also fine. So narrowly speaking, there are two types of UQ tasks. One is called forward uncertainty quantification. So this generally involves what is called sensitivity analysis, calculating, for example, local sensitivity or global sensitivity measures. And a more broader task is called uncertainty propagation. So that is, if your input is distributed according to some random or random variable or stochastic process in general, what does it imply for the output? So can you actually get the distribution of y? The other is called basically reversing the direction. So if you know your output, what can you infer about the input? Inverse problems do not have to be probabilistic. So you can just infer deterministically one x that possibly gives you y. But if you do it in a UQ way, the inference should be a distribution on x. But these are just the narrow definition of UQ, as we said. Here we rely on high fidelity computational model. But the broader way to look at uncertainty quantification is to improve the entire structure, the framework we just showed. So we can start looking at the different types of uncertainties in our scientific understanding. So first, we can use UQ to improve what is called known model form error. So that is the difference between your mathematical model and the ground truth. And of course, there are also difference between your numerical simulator with your experimental data. You can use experimental data to improve or update your simulation models. This is called calibration. And also you can use your simulation results, compare it with your experimental data to see if they match. This is called validation. There is also something called verification, which is defined as basically checking if your simulator is done correctly as defined mathematically in the algorithm. Well, the last part is about surrogate. So surrogate, building a surrogate to a simulator, this is also known as emulation or emulator. So basically you can understand surrogate and emulate are the same thing. So there is a big part in here. So if you can, so you can apply UQ to quantify, assess all these different types of errors and improve the entire understanding of a specific problem you're looking at. So here we'll look a bit deeper into surrogate modeling, which is one task of uncertainty quantification. So if you let's focus on the right part. So previously we defined this F mapping. If we take the input to be A and output to be U, this is the core part. But it is an operator, as I said. It maps functions to functions. Usually it's very difficult to handle. So what people usually do is that they parameterize both input and output. What's more correctly speaking, they parameterize the input to some finite dimensional parameters x, and you summarize the function output to be some finite number of quantities of interest or QRIs. So now you have this overall function f mapping from X to Y, that is actually now a function. So surrogates can be built the traditional ways to directly approximate the simpler f, a lowercase f function. But there are also approaches to directly approximate this operator. So usually, for example, one way to do it is to use Glerkin projection. You find a subspace to project it, the original system to a smaller dimensional system. So it still maps inputs to outputs as functions. So surrogate modeling can be built for both all these functions, all these mappings from the smaller f and also the original operator. You can also build surrogates on the reduced models. For example, if it varies with parameters. So all these can be approximated with surrogates. So here, I just mentioned reduced order modeling is one of those methods. You can also build statistical surrogates, for example, Gaussian process, which I will talk more later. And there is also polynomial chaos. It directly maps your input as a random variable to the output as another random variable. Currently, what is known as scientific machine learning, or SciML, they tend to use deep neural networks for surrogate modeling. So this has been very popular, and there's a lot of activity and different levels of success. So all these are different ways to do surrogate modeling. So now I will start with a specific study that's where we use surrogates. So to motivate this problem, we look at instead structural dynamics. So here we're looking at a canister, which you can separate into 3 levels. So from the left, A, B, C is the entire canister, and which has many slots. For every narrow slot, you put into a fuel assembly, which looks like a tube. And you can remove that tube to expose the internal structure, which looks like C. There are many, many internal, like fine scale pipes that stores. They're used to store nuclear fuels. And of course, there are many other parts of it, but that the fine details. So the takeaway is that it has ABC 3 levels of hierarchy. It is especially very complex. So if you discretize that using finite element, you can get very large degrees of freedom. For example, for this specific model, you can get up to 100 million. So which is really, really challenging to solve in the first place. And further to define the problem, what we want to know is to query what is inside, specifically whether the internal parts are intact or damaged by providing dynamic load at the bottom plate and measuring the response also on the bottom plate. So this is the problem. So you can think of using the previous way of thinking, you provide loading as input to this computation model, which is defined by parameters to get dynamic response. And the problem is to using the system response to estimate the parameters. Well, so this is just a motivating problem. And one way to do it is to build surrogates. And currently, for this specific problem, the best reduced order model is about 200K, which is pretty significant. But if you think about it, that is still a pretty large computational model. It cannot really solve the problem very efficiently. So we want to do better. Okay, so to understand this problem better, we first go into structural dynamics. If you discretize a structure using finite elements, the dynamic equations will look like this. You have your MCK matrices, and also F is your external forcing, and X is your displacement vector. And this system has a high degree of freedoms. Solving it, the computation time scales cubically to the end. So this is challenging, but if you have learned structural dynamics, there are these concept of eigenmodes, which are very useful. So mathematically, you are taking the K and M matrices and solve the generalized eigenvalue problem. So there are n numbers of this phi and omega pairs. So your omega is your eigenfrequency, and phi is your eigenmode or eigenfunction. So, well, this is neat in a sense that if you look at the bottom diagram, picture you have an arbitrary vibration, which is a function of space and time. You can decompose it as linear combinations of your eigenmodes. So this is useful, but more importantly, if you use what is called modal coordinates, basically using the phi to define new coordinates other than your original x, then you can derive these 1 degree of freedom equations that are separate from each other.
You're assuming Rayleigh damping, where your C is proportional to mass and K.
This is a modal damping assumption.
Rayleigh damping.
No modal damping. So here, what I did not define is the xi. The xi is the damping ratio.
It's viscous damping. Just viscous damping.
Yeah. It doesn't have to be Rayleigh damping.
Okay, the second vibration eigenmode, you're solving K Pi is equal to omega squared m Pi. That is the eigenvalue problem corresponding to C is equal to 0.
Yes, this one does not take care of C, and the C information comes into xi. And the assumption is that C can be diagonalized by the eigenmodes. Rayleigh damping is
alpha m plus beta k.
That's a special. It's a special case. Yeah.
And then you cannot diagonalize.
All right. Coming back, we have this as a single degree of freedom. So basically, you can picture that as the q sub I, that coordinate basically moves as if you have your basic MCK one-dimensional object. So solving this is very, very simple, and you can easily solve large numbers on. So that means you already, if you can calculate the eigenmodes, you have already simplified the solution a lot. So this comes into reduced order modeling in general. So I have previously the modal analysis, we have slightly touched on model reduction, but let's formally define what is model reduction. Here, let's picture your original model is a first order ordinary differential equation system, and degree of freedom is really large. So what we call a reduced order model is the model of the same structure, but smaller in size. So the smaller the dimension is, the faster it gets. But how do you actually get the reduced order model? A popular way to do it is called projection, either Galerkin projection or Petrov-Galerkin projection. So the idea is that you come up with bases that span certain subspace. And then operationally, you basically do, for example, your matrix A, you do a left and right product. So that shrinks the size of the matrix. It also shrinks the size of the U and C matrices. So this is how you get there. All right. So if you, with this general picture in mind, there are two traditional ways to do reduced order modeling for structural dynamics. So one is to take your eigenmodes and use a subset. So specifically, you can just simply truncate or do subsets by limiting the frequency band. For example, suppose you take, suppose you have a lower limit for the frequency, vibration frequency you care about, and also an upper limit, and you can use those to pick which eigenmode you want to keep. And then there is another way, which is arguably better, which is called modal ranking. Basically, you individually assign weights to those eigenmodes and keep those that are actually important. So on the bottom is one work along this line that is done in my previous group. So if you think about it, this type of reduced order models have an advantage, which is the reduced systems are actually separate. You actually diagonalize the ODE system, which are very easy to solve. But the downside is that you have to actually calculate the generalized eigenvectors and eigenvalues, which is really hard, which is basically not easier than solving the original problem as is. And also, if your structure has multiple hierarchies, basically many substructures, the eigenvalue or spectrum is very dense. So many things are close to each other. So those are prone to failure. Your generalized EVD solvers will fail, just don't converge. So there is to counter this downsides, there is a second idea, which is to exploit the matrix structure. So the original work is called dynamic substructuring, proposed by Craig and Bampton, who were at UT Austin. So the idea is that if you look at the matrices of structures, they have structure in the sense that mathematically, if you have a hierarchy for this for the physical structure, each substructure will be a matrix, and they can put together as on the diagonals. And then when you connect those substructures, the connecting parts fill up the matrices on the bands. So instead of solving the GEVD problem for the entire matrix, you can solve the substructures individually. So these come into phi sub s. And then you combine it with your boundary modes to get your projection bases. Well, this is the basic idea. And there's a variance, basically, if you have, for example, 3 levels or more than 2 levels of substructuring, you can repeatedly use the Craig Bampton from bottom up. So this is the idea. But these are generally the two structural ROM methods out there. So here, what I want to promote is this methods from system theory. So
Can I ask a question real quick? Go back to the other one. So we covered substructuring in this finite element course last semester, or 2 semesters. So there was a question that I'm not familiar with the codes. The question is, like, how do you know how to substructure? So the codes today actually adaptive, so they will do the work for you to take a large structure and kind of choose what the most efficient substructuring scheme is? Or do you still have to do that kind of manually, if you will? You call it adaptive substructuring.
Well, so that's what the literature calls it. Basic idea, you go from the simplest substructure. For example, each individual tubes in the canister problem, and then you solve that problem, and then you put it together into the higher level, and then you solve that problem, and you generally go to the global level. So that's how you always solve the simplest algebraic problem.
But could it be more convenient sometimes to take 2 tubes as a substructure rather than every one of them? Right? I mean, you have a choice how to partition the matrices, right?
Mm-hmm.
So
Your question is, given Ku is equal to F, can I reorder my equations written? Yes, there are algorithms. So he's answering different. So what he's asking is, let's say I have Ku is equal to F from a finite element. Can I reorder my node number such that I have this substructuring or maybe banded structure? There are algorithms for that.
So there are algorithms
Yeah,
that
yeah.
do that for you.
In fact, Abacus, what it does is before it goes and solves, it runs this algorithm, rearranges it, solves it, and then again inverts back.
Okay.
All right. So this is So how do we define a system in systems theory? So here, if we look at structural dynamics, they are called second order systems. So compare. So if you look at the equations here, what is different is that you not only have the MDK matrices, you also have the B and U. So these basically saying that you have a low dimensional input and also low dimensional output. And B and C are the mapping for the input and output. So why are they there? So basically, it's the idea that you don't. So when you solve the MDK equations, you are assuming you are solving a very harder problem than you actually are dealing with. But in practice, you do have those low dimensional inputs and outputs, then they're well justified. Why? The inputs are limited by how the discretized nodes you can access. For example, think about the chemistry problem. So there are many nodes. The majority of the nodes are inside the structure, which you cannot excite. So that automatically rules out most of the nodes. And also, even for those on the outside, which you can potentially excite individually, experimentally, you won't be able to excite every single point that you discretize. So it's going to take a lot of time. So that it means in practice, your input is much smaller. It also comes in the output. The same reasoning applies to the output where you collect the response. So that means your M and Q are much smaller compared to the most general case where your B and C are actually just identity matrices. So the insight is that given this major dimensionality reduction, you get major simplification for the problem. Because you're reducing the dimensions of the input and output, the functions will be much simpler to approximate. So that means you are possible to do more things. So without going into much detail about system theory, one thing, so let me just go without this part. So let me look at what the previous two ideas in structure and structure reduced order models are doing. So without defining transfer function, it is a function that's on complex domains. So if you look at, for example, if you have only a single input and single output system, it is a complex function. So and it's a rational function, it has poles. So basically where the value goes to infinity. So for a stable second order system, the poles are conjugate pairs. That means they mirror across the real numbers and they're all to the left. So they all have negative real parts. Well, that is not important. But so if you are following the truncation by frequency, the idea is that you are drawing a circle or maybe two circles as your lower bound and upper bound. You are only keeping those in the band, in those two circles. But the idea is that the location of the poles only depends on your MCK matrices. They don't vary with your inputs. The residuals actually change with your inputs. So that means there are some of the poles are not that important. So you can subset that even further. But in systems theory, so what you're actually trying to approximate are the values for the transfer function on the imaginary axis, which is also known as the frequency response function. So if you know your goal is to approximate the function on the on the imaginary axis, you don't have to care about the poles actually. So the first idea is called rational Krylov. So what it says, if you plot the frequency axis and the response, you basically take points and do interpolation. And the more points you collect, the easier, the closer you get to the actual function. So that is basically interpolation. That is, which is good. But a better way, in a sense that further dimension reduction, is called balanced truncation, which uses concepts about energy, and they all have second order variance and frequency limited variance. I will not go into the details, but the idea is that comparing all these methods, you can come up using system theoretical methods to get one specific method that is it achieves low time and space cost and also high accuracy. So this is the methods we'll be using. But that method, all these methods do not allow variation in parameters. So that means we don't really know how the basis varies when your system actually depends on some parameters. So the idea is that if you can directly emulate the mapping from the parameters to the bases to enable what is called parametric reduced order model. So this is a work I have done, which basically it's abstract, and what it solves is actually a generic way using a new Gaussian process model to predict subspace valued mappings, and you can use that for reduced order model. So this is so let me show the application of this method on a simplified structure here. So if you recall the nuclear canister, you have these. The second level is a what is called nuclear fuel assembly. They consist of many tubes organized in a vertical alignment. So we take that and simplify it to test out the idea. So we got this original model at level of over 300K degrees of freedom, and we set one parameter to be the Young's modulus of the horizontal plates, which you see as in black. So this is the result where we compare the original model and the reduced model. So on the horizontal axis are the frequencies. So basically, we are taking the we are using the frequency response function, and the vertical is the norm of the transfer function. So basically, you can take the lines to be identical to the system. The closer the lines, the better the approximation. And here we're focusing on a limited frequency band. And so you see the red curve is the reduced order model using the previously defined system theoretic reduced order model. And we have a dimension reduced to 60 compared to 300K. That is a lot of reduction. And there is a very nice matching within the frequency band, and beyond that, we don't really care. And this is another way to see it. The error is plotted instead of the absolute value. So you get almost below 1% error everywhere on the frequency band. So this shows combining the local reduced order method and the GPS method, we get the errors for when we change the parameters. So the horizontal axis now is the parameter and vertical is the error. So the blue lines are the results from the GPS method, and black is considered as the ground truth, the best possible. So we see that compared to the current best methods, the GPS method is more accurate. And let's apply it to a forward EQ problem, where here the black curves are when you vary the input, sampling the input from a uniform distribution defined here. And for every input, you get a response, which is the system. You also do the sampling and calculate the true system function. And you see that you have this accurate, almost one-to-one matching to the ground truth. So this means that you can use the surrogate very with high confidence for parametric studies. So finally, we look at the computation cost. So the last line is our method. Compared with ground truth, the reduction in time is 4 orders of magnitude, and you also save space. So that means you're not only accurate, it also saves both time and space cost, which is what we would like to have. Well, so this summarizes the second part of the talk. So what we discussed is that there is an efficient model reduction method from systems theory applied to that structural dynamics. And we used a method called GPS for subspace prediction, using that to construct parametric model reduction. So currently at my group, there are 2 lines of work. One is, well, if you know Gaussian process, that has been around for a long time, and GPS is not the just direct application, but it is new modeling using Gaussian process. I think Gaussian process or stochastic process models in general are very powerful, and the current ways of using it are limiting, well, in a sense, limited. So one way is to use stochastic process models to approximate new objects. For example, not only subspace, we can also model other unconventional objects that are of interest to scientific computing. Another newer line, as I discussed, is that so if you think about the solution operator, it's called an operator, and if you want to approximate the operator directly for surrogate modeling, it's called operator approximation. And if you do machine learning using for that, it's called operator learning. And it has been of recent interest a lot. Last week I was at CIVE CSE, and there are a lot of talk about operator learning, and I came up with some idea which directly uses a stochastic process, but in a more use the stochastic process for operator learning. And I think it is a very promising way for this task. So that summarized my my talk.
Time for question. Yeah.
I think a question about the model reduction, because as I saw in your example, it was structure. You use the so could these techniques also be applied in medium, for example, like soil? Let's say you have a structure, but you want to reduce the medium in which it is surrounded. It might be air, water, soil. Can those techniques also be applied there?
I need to know what's the governing equation there.
Okay. So, okay.
Yeah, I mean, he talks about maybe a soil that, let's say you have a numerical domain that is very large, typically for soil modeling or food modeling, we can basically model like a parts. The boundary model, the boundary is kind of surrogate model so that we can reduce the computational time. I don't know if that makes sense. It's not subject model, but infinite elements, you can use infinite elements. So let's say you have an unbounded domain or whatever, so you can use infinite elements and solve like a finite dimensional problem. But that may not be necessarily a surrogate model.
So with radiation boundary conditions and things like that.
Yeah, very nice.
You got to make sure you don't get waves coming back and stuff. You have to dissipate the waves.
Can I ask one question?
Yeah, sure.
The students don't have. So, but even the name suggests, right, when you have subspace, you're assuming that your data is in a vector space or it's in a linear manifold. But what about my data is not necessarily linear? Why I'm asking here is recently, last 4 years or so, there are papers based on machine learning or deep learning or neural networks where they say the subspace methods are not necessarily, cannot capture when the data is not a linear manifold. So what is your take on it?
Yeah, when I started this research, I'm pretty much limited to the old literature, but I think I have a better understanding of the entire field. I think one promising way to do it is use transformations, linear transformations. So basically, there are different ways to call it. Basically, you transform input using a linear map, and then also transform your output using linear map to another object. And for these called latent space features or quantities, you can model it using low dimensional linear maps. And how do you approximate the linear maps? There are different ways to do it. If you ask many of these IML people, they will use neural networks, but you can also use, for example, random features, which basically say you draw randomly nonlinear maps and do that embedding. And then within the latent space, you can do a linear map. So basically, this solves the nonlinear nonlinearity issue in the problems. And the good thing about linearity in linear problems is that we have very good methods to deal with them.
So how about a completely different, for example, structural engineers, we have been doing this reduced order modeling on these kinds of stuff for a very long time. Let's say you have continuum mechanics equations, people don't want to solve them. The develop beam, the Euler beam is some sort of a reduced order model of elasticity of shell. So the question here is we can do at a mathematical level, at a numerical algebra level, creating the surrogate model. But there could be another level where we can do even from a mathematically deriving like a equivalent of Euler beam for complicated problems. So where does this type of dimension reduction fit into your overall picture? The classical example is instead of solving a three-dimensional elasticity, under some cases, under some assumptions, I can actually get a very good result with the Euler beam.
Yeah.
That's also reduced order modeling. So in this paradigm, where do these methods fit in?
So I have a word for it, and let's go to here, for example. So I think you can call that you can consider that as simplified physics. Or basically, for example, the simulators have different levels of complexity. You can call something as high fidelity model and something as low fidelity model. If you simplify a lot, you get a low fidelity model, but that's also you can call that as a low fidelity model itself without calling it a surrogate or reduced order model.
Again, this one thing is confusing is, see, uncertainty quantification is independent of surrogate. I don't need a surrogate to do answer. It may be useful, but when we try to combine uncertainty quantification with surrogate, it gives an impression that we need a surrogate to do uncertainty quantification. In fact, I can take away the right part and I can do uncertainty quantification on the simulator on any of the aspects. So we agree that a surrogate is not necessary to do uncertainty quantification.
I currently don't think so, because if you look at all these methods, for example, Holland chaos, it's just disregard the high fidelity model, just maps the uncertain inputs to the output. And so basically everything are bypassing the high fidelity scientific computing code. And if you directly do it, the issue is that, for example, if you do Monte Carlo, it's basically not possible because you're running high fidelity codes many times, and that is not, you don't have the computation power to do that.
It's computationally interactive. It may be convenient, but I can define uncertainty quantification without appealing to surrogate. That's my point. Last question. If we go to the first figure, quite intrigued by that. So one of the major errors is actually between the system truth and measurement. Let's say there is something, some phenomenon is going and I'm trying to measure it. In fact, there can be an error between the system truth, ground truth versus measurement. So did you consider, like, will the framework be able to guide some of those things?
So how do you track the error propagation, which involves errors in the measurement, errors perhaps in the physical modeling? I mean, isn't one of the powers of uncertainty quantification that you could kind of quantify the error propagation in your modeling?
Yes.
I think it's the examples you did don't have that in it, but in general, in the big framework, here's an example. People use uncertainty quantification in molecular dynamics. And it's just the Newton problem, right? You have particles that are interacting through some potential fields, but there's assumptions and uncertainties at that level. So you sort of don't need a surrogate model. You're trying to quantify the error propagation in the molecular modeling of a solid by looking at the propagation of the error as it's contributed by all the little uncertainties that you're modeling. So what would I need, like a surrogate model? I mean, the equation is simply F equals MA.
Yeah, for example, if you have a beam, okay, I have a cantilever beam and I want to measure the tip deflection, but I have some uncertainty in my Young's modulus. Don't you think that is also some sort of uncertainty quantification where I want to know how much the tip displacement is affected due to my uncertainty in Young's modulus? I don't need another surrogate model to do this, right?
Well, I understand your point, and I think well, I think the point is you can take out this, but that the uncertainty quantification is something more. If you, for example, if you define your fidelity at a certain level and you want to have uncertainty quantification, you have to model the probabilistic way, and I think that's an overhead. Well, that's considering if you fix your fidelity level. If you start with something that is really low fidelity, then that's fine. You don't need a surrogate. Ultimately, suppose you know everything, like every location of the atoms in this table, then I can basically I know everything. There's minimal amount of uncertainty there, but you're basically trading the complexity with uncertainty. So basically they're always a combination of both. So I think if you want to do uncertainty quantification, somehow the information you assume the model should be small or simple. That allows you to model the rest with probabilistic model methods.
Well, we could also talk afterwards. Any additional questions? In the model, in the nuclear rods, what is that? I missed it. What was the uncertainty? Is the Young's modulus?
Yes. So the Young's modulus is the plates.
Of the what?
The plates that holds the tubes.
And why would they be uncertain in that application? I mean, that's material that is designed and tested. That's just a toy problem, or
yeah,
because I mean, we know what the modulus is of this.
Yeah. So the actual quantity of interest will be what is the uncertain parts or parameter is the spring that connects the.
Okay, that I believe. Okay, so the
yeah.
connection is really uncertainty,
yeah.
right?
Or is it because the radiation, maybe over the time it is bombarded with the radiation, maybe the properties change, maybe that it could be the source of uncertainty in the Young's modulus. I'm thinking that. Yeah.
Well, that means that the result actually is just a for example. So the setup is artificial.
The first lecture I heard, just as an anecdote on uncertainty, was by a scientist who worked for the NSA, and he was one of Roger's friends, and he said, "Okay, let me explain that to the people in the audience." He said, and again, I'm very naive about this field. He says, uncertainty quantification. Here's the problem: we have a bunch of nuclear bombs on the East Coast that have been there for 60 years. They're material degraded. We don't have any differential equations to describe them, their response, but we have to put them on a train and bring them to Armadillo, Texas, right? Which is where they dismantle all the nuclear bombs in the country. Don't go too far. Don't go to that place. And you have to know what the probability of an explosion on the train is. Because that's a classic problem of uncertainty quantification, where you don't even have the differential equation, you don't have the physics, but you have to come up with a model. And then come up with a confidence level in your model so you know what's going to happen to those bombs as they go across the United States. So those kind of models, you don't really need a model, right?
Yeah,
You sure don't need a surrogate model, perhaps, right? Because you actually don't have a model.
yeah.
So
Well,
could you do uncertainty quantification without a model?
yes, well, depending on our starting point, in the lineage here shown, it's pretty much just one thing after another, but but you don't have to start with first principle and
Right, exactly. So,
and you don't have to start with high fidelity model numerical code. You can directly use data, what is currently known as data-driven engineering. Well, of course, that's you can be part of that, but still, it's a very new field, and people are trying different methods, and we have to see.
yeah, I mean, that's what I agree with you. I went on this call to the students. I mean, if I was 50 years younger, I get into this field because those problems where you don't, because this is a nice example you gave where you actually have the differential equations, right? But I also find very exciting that you could apply this field or develop this field where you actually don't have equations and you have to figure out ways, like you said, whether it's data driven or whatever, where you have to come up with an engineering decision,
yeah,
and be able to have some measure of the confidence in your decision, right?
Yeah, so basically, if you heard there are methods using deep learning, for example, operator inference and deep neural nets. They're basically trying to use data to infer the solution operator. And I think, but all of those methods don't involve uncertainty quantification. They're deterministic. So what I'm trying to do currently is there should be a publicity way to do that. Just use data, and I think that's a very exciting field. Yeah.
Anyway, I'm sure you'll answer all the questions if they come
Yeah.
up.
Yes.
Thank you.